Well, good afternoon, everybody. Thanks for coming along to this final plenary session of the second day of ICSE 2023. We've got three very prestigious award winner talks this afternoon. The Harlan D. Mills, the most influential paper, and the ACM SIGSOFT Outstanding Research Award. So I think these are excellent speakers and very, very impactful research. It's a real privilege to have them speaking today. And I'll start off by handing over to Paolo, who's going to introduce the winner of the Harlan D. Mills this year.
Good afternoon, everyone. I'm Paolo Tonella, and I'm going to chair the session on the Harlan D. Mills Award. And let me find out how to progress on the slides. Yep. So, this award was established in memory of Harlan D. Mills, and the idea of the award is to recognize long-standing, sustained, and impactful contributions in our area. So we have to recognize the importance of our giants, and if you have a look at the list of the previous recipients from 1999 to the last year, you will recognize a lot of giants in the list. So, for this year's award, we have formed a committee consisting of 5 people, and I take this opportunity to thank each of them because of the work they did. It was very appreciated, and I had the pleasure to head the committee. So the process for this award consists first of the collection of nominations. For this year's award, we had 7 nominations. Then the program committee, the members of the committee, of the selection committee, declared their conflicts. And then every non-conflicted member expressed their preferences in terms of the top 3 rankings. The top one was granted 3 points, 2 to the second and 1 to the third. And in this way, we got a short list of nominees. And then we had a discussion for the selection of the actual awardee from the top 3. In reality, this year there was not much discussion because there was quite an ample consensus on the winner. Before moving on and announcing the winner, let me tell you something more about nominations. As I said, it's very important that we give recognitions to the main contributors in our fields, to the giants, and you have an opportunity to nominate somebody for the Harlan D. Mills Award for the next year. The deadline for the nomination is October 1st, so there's quite some time to prepare the nomination package. So please consider doing that. So now I hand it over to the IEEE Computer Society President, Nita Patel, who will announce the winner for this year.
Thank you, Paolo. It's my privilege to announce this year's winner, Professor David Harlan, who has provided sustained and impactful contributions to software engineering practice and research. Many applications use his benefits from the work he's done and implemented, specifically the impact of state charts and live sequence charts on software engineering has been quite profound. I'm sure we were just talking earlier before the starting and thinking back to even within my industry having used state charts in software design. I'm very honored in this contributions and honored to congratulate Dr. David Harlan on this award. Please join us.
And now we will have the pleasure to listen to a retrospective talk by David Harlan on his contributions to the field. Please.
What he didn't tell you is that I bribed the committee Thank you very much. Thank you for the award. This is going to be, it should have been a 1 hour long presentation, but I'm told it's shorter. Someone once went to Bernard Shaw and said, I've only been given 30 minutes to talk about this and that topic. How can I get everything I know about it into 30 minutes? And Bernard Shaw said, speak very, very slowly. So most of the slides you'll see here are over 40 years old. Some are 25 years old, and a couple are newer. So late 1982 to mid-1983, I consulted at the Israel Aircraft Industries on an advanced avionics project just for a few months, 1 day a week. This is what success in a software development project should look like. I don't know if you can see my... Anyway, everything should go fine. You can see the age of this slide because of the 2167 standard. Everything is fine, it's done on time, and there are no people here because everyone is beyond the horizon because it's been so successful. What I discovered, and I'm sure many of you have, is that the real process looks a lot more like this, with all kinds of problems and pitfalls and places to get stuck. Again, you can see Ada here, which gives you a feeling for how old this slide is. The problem is that here there are no people either, but for quite different reasons. They're all stuck right down at the bottom left of the slide in the specification gridlock. If we zoom in, we see people scratching their heads trying to understand requirements, specifications, whatever. And to be slightly more responsible about this point, by the way, the person on the left was drawn by the artist in our department as a man, but of course this was in 1982. You cannot show a slide like that. So I added some hair to make it gender balanced. And so on the one hand, you have the group of people who say what they want or think they know what they want. And on the other hand, there are the people who have to put that, make something out of it, build the hardware and the software. Those are the implementers. And the problem is not just how to write the specification. The problem is the communication between these two. The communication is not just a question of language. It's a much deeper issue, as I'm sure you know. And the one thing that I decided was the central issue here was specifying behavior. There were pretty good ways to specify structure and the pieces of the system, and maybe a little bit about what each of them should do, but to specify behavior clearly so that the people on the left can say what they want and the people on the right can understand what the people on the left want and then go and build a system to do this clearly and precisely. Those are the two keywords. That is, and that was, for me doing that consulting, the heart of the problem. And I want to show you something that I've shown many, many times for decades. This is part of a real spec, not an avionics project. It had to do with some chemical plant. And this document was about 600 or 700 pages long. I had it in my hotel room at some point. And I tried to find one small but crucial piece of behavior and to see how it was reflected, how it was written up in this document. And I found that piece of behavior appearing 3 times in the document. Everything on this slide is accurate except for the page numbers, which I forgot to copy, so I made them up. Very early on, there was a clause, 2.7.6, this is how these documents are built, on security, and it said if the system sends a signal hot, then send a message to the operator. Later on, much later on, there was a section on temperatures where it said if the system sends a signal hot and T is greater than 60 degrees, then send a message to the operator. The real gem was the 3rd place, which was right at the end of the document. There was a summary of some of the crucial behavioral points in this system. And there it said, and this is written down exactly, including the lack of punctuation, when the temperature is maximum, comma, the system should display a message on the screen unless no operator is on the site except when T is less than 60 degrees. Now, prior to this work, I had been trained and brought up and did my PhD in logic. And as a logician, I have never, until this very day, been able to figure out whether this 3rd statement is equivalent to or implies or is implied by any of the previous 2. Now, this is not a joke. This is the document that is used by the programmers to build the system. And then go be surprised when things blow up and things don't work the way you want. But let's get back to that consulting. And I made some copies of my notes from 1982. And I'm doing this just to give you a little bit of a feeling for how this visual language developed, at least in my personal mind. So the first attempt I made when listening to these people speak about the system was to use a logical formalism. I said, I grew up as a logician, or computer science logic, and I started to use modal-style temporal operators. So that's my notebook, and if you look at the bottom right, can you see these arrows? Yeah, so on the left you see, this kind of logical formalism. On the right you see some modal operators. This was my first attempt. The second attempt, I tried to make up a structured state-based language talking about states and substates, and this looked more or less like this. You can see the indentation, but notice the doodling that I used on the right, like to scribble little pictures to explain to the people I was trying to talk to what I really meant in this more rigorous state-based structured language. But then over a few days or a few weeks, the doodling started taking center stage. And then instead of writing these things down, I used to draw these pictures. And here you can notice the beginnings of a hierarchy with states inside states and transitions that go from lower levels to higher levels and so on. Also note the first use of this concurrency operator in state charts, orthogonality, which I denoted by dashed lines. And here I was explaining to them what it means, and on the top of this, over here, you can see an and/or tree. So I explained to them that an orthogonal state, and within it some substates, is really an and of ors. Then I did things to enhance expressiveness and to make things more improved, and things began to look a little more orderly. Note here the first time that I used orthogonality within orthogonality. That's very important. So people say, oh, state charts is just a bunch of communicating state machines. Well, no, because you can have the orthogonality on any level. So the state at each point is a vector which is flexible. It can get smaller or larger as you move in and out of these states which have okay, so that's what I say here. State is a flexible vector of atomic states. And notice that on top, mathematically, I use a Cartesian product, which of course is the natural way mathematically to describe this orthogonality notion. And then it started coming out as a language. I wasn't thinking of a language, I was thinking of drawing pictures that make sense. And then I started to define things more properly, at least for the beginning for myself. And this is the first time that I decided that the interesting notion here is not a start state, because the system does not necessarily start in this state, but it's a default state because it can occur on any level. So the system can be working for a year, and then you go into some lower level state. It has some substates, and what you get there is not a start state, but the default state, which is really a generalization of the notion of a start state in automata theory. And then I wrote a document in September of 1980, I think this should be 82, actually, maybe 83, for the use of the avionics people. And so here is really on the bottom, it's written in Hebrew, I apologize, but the first attempt to use this little language, which wasn't yet a formal language, for some application. And I'll just translate. On the left, you see, so this is a big orthogonal component, and on the left you get the modes of operation of this particular aircraft: air-air, air-ground, auto-navigation, and being on the ground. And then here you have the radar, the INS, the communications as orthogonal components. In early 1985, I took a plane trip with the late Amir Pnueli, and by the way, he's no longer alive, as you know, but our offices are about 10 or 12 meters from one another at the Weizmann Institute, but I used to meet him mainly in Australia, in New York, in Paris, and on airplanes. And so a plane trip with him, we discussed, so he liked this idea of state charts a lot, and we tried to pinpoint what kinds of systems is this good for. Not necessarily for doing a sorting algorithm, so what is it good for? And the result of this 1 hour discussion was the notion of a reactive system. And we decided not only that this is a good term, a reactive system, but that this is really the critical issue in these kinds of complex systems. So a reactive system is not transformational, it doesn't take inputs, blah, 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 and produce outputs, but rather it has inputs and outputs all the time. And you have to respond sometimes in real time, sometimes concurrently, sometimes in a distributed fashion. But the bottom of this slide, the point is that whereas the green versions are all usually easier than the blue versions, concurrency is more difficult than sequentiality, real time is more difficult to do than lazy time, and things that are distributed are more difficult to specify than things that are centralized. But the more important distinction is between being reactive and being transformational, and reactive can be any of the things on the bottom, just makes things a lot more complicated. But the crucial issue for which this problem of specifying behavior is really, really difficult is the notion of a reactive system. And at the time, this also is a very old slide. There were many, many examples of reactive systems. There are many more today. But even then, I already identified that things like biological systems and financial and social systems are to be included in this definition of discrete reactive behavior. From 84 to 87, I tried to get the state charts paper published. I don't know how many of you know this. It took me 3 years to get this paper published. The first version had a slightly different title, State Charts, a Visual Tool for the Design and Specification of Complex System. The date on top here is December 1983. The graphics, so if you get your hand on the hard copy of this paper, I managed to convince the journal to incorporate a folding picture of this citizen watch, which opens, I think, 3 or 4 folds. This was my handwritten version of that example, and the paper was rejected one time after another from Communications of the ACM, from IEEE Computer, a second time from IEEE Computer, a special issue on something, then from IEEE Software. I have a whole bunch of interesting editor and reviewers' reports. Some of them didn't even read the paper. They said it's too long, too many pictures. Some of them said, oh, this is all easy, it's just finite automata. Some said this will never be useful. And finally, I gave in to Amir Pnueli's prodding to have this published in a rather obscure journal in theoretical computer science called The Science of Computer Programming, of which he was one of the editors. And even it took him 2 or so years to get reviewers to agree to review the paper. So it was finally published 3.5 years after I first submitted it. But at the time, I don't know how many of you were around then, we used to get little cards asking for reprints. I have a whole pile of requests of those. And it was published in this journal, Science of Computer Programming. A slight error beneath the title and the author. It says when it was received, it should be December 85, not December 84. This rather painful process, I think, is especially interesting, given the following, and excuse me for the next couple of slides, but I thought it would be, especially for the younger generation, do not give up. If you feel something you're doing is good, just push and push and push until it gets published, with the hope that no one will do the same thing earlier and get it published elsewhere. So in September 2002, there was no Google Scholar then, there was something called CiteSeer, and the State Charts paper was the second most widely cited paper in computer science, which is nice. But what's even nicer is the third paper was the RSA paper, which has since then, of course, overtaken State Charts in popularity, the Reverse Shamir Edelman paper. And these days, the paper has over 11,000 citations. The next thing that happened that is relevant to this story is to think of state charts not just as a language for describing the behavior of a single component or a single piece of software or hardware, but to embed this in a structure. And of course, a very famous way of doing structure at the time was functional decomposition. So we defined activity charts, which are really functions, components that are functional, and we link these with state charts in a non-trivial way. I mean, today maybe it's very easy, but at the time it was, and we designed and built a tool called StateMate, The paper on StateMate, which I'll mention in a minute, has 7 authors. One of them was Amir Pnueli, Levi Sherman, Michal Politi, and 2 other people who were instrumental. By the way, here in the audience, one of my late-blooming PhD students, Raz Yerushalmi, was not on that paper, but he joined iLogix a little bit afterwards and worked on StateMate quite a bit. I like this photo. I know you don't believe this, but this is me explaining visual formalisms in 1984. And so visual, you can see the visuality. This is state charts on the blackboard, on the whiteboard. And you can see the formalism because when I had to explain the formal semantics of this, I often used things like temporal logic. Another interesting part of this picture is the proof of how long ago this picture was, 1984. So this is not exactly what you see these days. I want to say a couple of words on these 2 terms, visual and formal, leading to this term of visual formalism. Visuality, a good visual language, does not start with things that are round or square or yellow or red or thick or thin, but things topological. Are these 2 things connected? Is one inside the other? And so on and so forth. Then, of course, you can use geometry. So a square might be different from a triangle. A thick line might be different from a thin line. And then you can use icons, you know, for a file, for a clock, for whatever. A lot of times people say my language is visual, and they're really just using icons instead of keywords. And this is fine, but the human brain understands topology very, very well if presented in 2 dimensions or in 3 dimensions. So if you're trying to do a visual language and you want it to be useful, and the usefulness of such languages is like the proof of the pudding is in the eating. You can't force people to like your language. For example, there's a big difference between Petri nets and state charts, although mathematically they are different. And one of them is slightly less useful because there's no natural notion of hierarchy. And even if you don't care to explain the difference, the proof of the pudding is in the eating. And I think one of the main advantages of state charts is the fact that topology is a key feature of the language. And of course, formal, I don't think I have to explain this to this audience. Again, this is a very old slide, remember, from the 1980s. But at the time, there was a myth that a formal specification is a formal-looking specification. The more Greek letters you have in your specification, the more impressive it is. And of course, that is a farce. That's not true. A formal language is one that has a rigorously defined syntax, a rigorously defined semantic domain, and a rigorously defined semantic function, taking the former to the latter. There's a paper that I wrote with Bernard Rumpe a few years back that you can look up, which we explain this notion of what formal and semantics really is. And I mentioned StateMate already. I want to pause on this for a minute. So this tool was built in 1986. It was, and this is essentially a quote from one of the awards that it received, the first tool to offer comprehensive model-based system development with fully executable visual formalisms, in this case, state charts and the activity charts I mentioned, for behavior. And because this is the ICSE conference, and this is an award session, so this paper was first published in ICSE in 1986, and at the time there was a best paper award. I don't know if this is still the case, where the committee chooses the best paper presented at the conference. But then 10 years later, the same paper got the award that will be presented soon, the most influential paper award for the same paper at the same conference in 1996. And at some point in between these two, the paper was published in IEEE Transactions on Software Engineering. But really the highlight in terms of the recognition of this paper was that the 7 of us received the 2007 ACM Software System Award. As an aside, I was chosen by the authors to thank for the award, and one of the things I said there was that it's interesting that you've chosen to give me a Software System Award, and I haven't written a line of software for 25 years myself. So students, yes, and I'm not sure that came across very, very well. I hope this works. This is a clip pre-YouTube that I've been using for many, many years to illustrate the advantages of a model of behavior that can be executed. And I hope this works, and I hope you can also hear the audio. So this is the real thing. This is the simulation. Yeah, I agree. That's quite cool. One mishap here was that we had a detailed document giving the state chart semantics as embedded in the StateMate tool. This was an internal iLogix document. I didn't think it was that important to publish, and we got hit by several people who said that the language has no semantics, or you can interpret differently. And so only 10 years later, we finally published a real paper giving the StateMate semantics of state charts in transactions and software engineering methodology. 1992 to 1995, we defined the object-oriented version of state charts, which was, of course, a lot more attractive because objects were becoming center stage, and we built the object-oriented variant or version of StateMate, which had different features. In particular, it was less an interpreter and more of a compiler, and this was done also at iLogix with Eran Geri, and again, I think Razi Yerushalmi is here, and he was one of the key people working also on that at the time. From 1996 on, I'm giving a very brief list of several of the things that I've been involved in. So at the beginning, when I decided to give this talk as a retrospect, I was not going to concentrate on this, but I do want to make a list of some of the things that grew out of this early work. I mentioned already biological modeling, so I've spent 25 years doing many projects on modeling complex pieces of biology, mostly using state charts, but not always, sometimes variance and sometimes scenario-based. And if I have 2 minutes, I'll show you an example of that. And then was mentioned already scenario-based programming and life sequence charts with the two very, I think, elegant ideas of playing in behavior from a GUI and playing it out on a GUI. One of the key figures here is Shachar Maoz, an ex-PhD student who is also here and I think has 3 papers at this conference. So the children are making us feel good. We did some work on a natural language interface to these kinds of programming, and I think a very interesting idea of show and tell, where to explain how this works, I show you stuff, but I also tell you about it, and we merge playing with the GUI with natural language to specify behavior. One important issue is to link a state-based approach with a scenario-based approach, link in a deep way so that you can build a system. Parts of it are specified using states, part of it are specified using scenarios, but the entire semantics and the execution is smoothly connected. I've done some work on using state charts to specify how people draw pictures and how they play music, with some applications to arts and music therapy. I would recommend, so in red here there is a paper from 5 years ago in IEEE Computer. I would humbly recommend that you take a look at that paper because it gives kind of a vision for wise computing. Yes, I know about ChatGPT, and I know that people are trying to program using ChatGPT. We're also looking into that, but still this does not shed the responsibility we have for defining languages and methods for doing real software and systems engineering. And I would really recommend that you read this easy-to-read paper. There are 2 demos linked to inside the paper of how we see this thing happening. These days, we're trying to enhance deep learning networks with scenario-based programming. One example is to give scenarios that depict the restraints, the constraints, or the specification of what you want of the system. And this is not exactly true verification of neural nets. It's not exactly explainability, but it's taking steps towards making these things less transparent. And finally, something that's not directly linked to this, but I wanted to mention, nevertheless, as a paper we just uploaded last week to arXiv on the question that I think is the much more timely and important issue to be generated or to be spawned by or to be inspired by the Turing test, which is not to tell whether a computer is intelligent like a human, but to tell whether I'm talking to or communicating with a human or with a machine. And here we don't, it's not a technical paper, it's a very, very easy read. We simply raise the issues. Do you always want do you always want an agent to let you know whether it's a person or a machine? If you know, does that change your behavior? What are the issues? And so we're trying to surface things. Most of what is written in this paper is almost obvious, but we just finished it, at least the first version, and I recommend that. And now, if I have 2 more minutes, I'm going to try to show you an old, 20 years old demo of a very complex piece of behavior specified solely with state charts. So this is differentiating T cells in the thymus. Many objects, each object has a state chart, complex internal behavior, a lot of interaction, and a lot of movement, and an enormous amount of biological knowledge that had to be assimilated and modeled, especially by our PhD student Solefoni at the time, almost 400 papers. And we used state charts in Rhapsody, connected to Flash, any of those of you who remember that, via a novel reactive animation technique that kind of lets the system run and does the animation as a side effect of that. This is what the front end looks like. I won't have time to explain the diagonal things. They're not just lines, they are epithelial cells. All the circles in the various colors are these cells. They all vie to reach this area over here on the right, which is when they become fully fledged grown-up T cells. And they compete. In order to do that, the chemistry and the biology of the competition I won't be able to get into. But I want to show you the model in execution. And when you look at this, just take into account that each of these circles is a very complicated state chart, and they're all running in parallel. The thing you will see now about left of the center in the cortex is gradually these cells try to communicate with the epithelial cells. This has if you manage to interact correctly with the epithelial cells, you will get the ability to then jump over to the medulla on the right in this picture and become a fully fledged T cell. The little X's you see are apoptosis. This is altruistic suicide that I, a cell, will commit in order to let my brethren and sisterin succeed. And this is just a real-time, not real-time biology, but real-time in terms of the model execution of the system. While this is happening, here is a very tiny piece of a small part of the state charts of 3 or 4 of the cells as they operate, so you can get a feeling for what's going on underneath the surface. So you have 5 T cells, just the top 2 or 3 levels of the state chart, and on the left top there's some control unit, and you can get a feeling for the dynamics of what is going on beneath the surface. And finally, I want to show you this, which is a lot of people have said you spend such a lot of time and effort on modeling biology just to get nice pictures and nice videos. Well, of course not. You really would like to make biological discoveries. So we have made quite a few, nothing on the Nobel Prize level. Someone recommended that I add yet to that, but that would be much too presumptuous. Mid-level discoveries at the best. And one of the things we discovered here had to do with a particular chemical which gives these cells the ability to compete and elbow each other to get to communicate with the epithelial cells. And I want to show you what you'll see now is 2 runs of the system, on the top and on the bottom. On the top is a normal run, done slightly slower than the one I showed you a minute ago. On the top, and on the bottom is the same system where we essentially shut down this chemical. So it's a little bit like taking from all the researchers in software engineering, shutting down your competition gene. And of course, many of you would not bother to come to Melbourne for this conference. Many of you would be doing other things in life. And what you'll see between the top and the bottom is in the top, you'll see, as you saw earlier, the cells competing, this fierce competition on the left of the center area of the picture. And on the bottom, they couldn't care less. You know, they kind of go around. Some of them, by chance, become T cells. Some of them don't, and they don't really care because there's no incentive to compete. So you can see this already, the difference between the top and the bottom. And so these kinds of things for me are very exciting, as are all the other applications. And all in all, it's been a great 4 decades or so, and I've had lots and lots of fun, and I hope to have some more fun. And thank you so much for the award, IEEE Computer Society, and all of you for listening. Thank you.
Thanks so much for the great presentation. I've really enjoyed your work over many years. Invented some visual languages myself, but I guess one of the issues I've found is not specifying the formalism aspect perhaps as much as we should have. How critical is that duality of a visual language that, I guess fits the cognitive state, the topology, etc., and linking it to a strong formalism? Has that been absolutely critical for the success of state choice, do you think?
Yes, it's been critical, and of course the question is, what is the medium in which you write down the semantics? It can again be formal looking. The way we decided to do it is to give an operational semantics, and you can complain about that if you want to. It's always, but then you can also complain about a lot of Greek letters in a formal looking specification. I'm not trying to judge either way, but yes, and I did admit that we did a lousy job in putting forward the semantics of state charts in a timely fashion, and we got flack for that. But there are many variants of the language. The two main ones are the StateMate version and the Rhapsody version. The Rhapsody version also has a paper that's been published with the semantics. And yes, you don't want to let people use this if they don't understand what's going on. But sometimes people still don't. I just got email about a week ago from someone who asked about a particular issue in state charts. It wasn't clear to him what the semantics was, and we had to show him in the semantics where this appears and how it works out.
There's no other question from the audience. I would congratulate again David.
Thank you. Thank you very much.
And please join me in congratulating.
Patty and myself are the program chairs of ICSE 2013, and as if you agree to be program co-chairs of ICSE, 10 years later, there's another job to do. And as David has already said, the most influential paper award of ICSE, I think, is one of the most well-established awards of conferences. And the way it works, I will describe in 1 minute, not more. You select a committee. This was our committee, and before I go further, I want to thank the people who contributed to that. Because believe it or not, selecting the most influential paper out of around 80, 90 accepted papers is not so easy job. I put a few bullets, and Betty and myself put a few bullets about the selection process. You can read. I'm not going to explain. The main thing about it, in my point of view, is that the selection was really a common sense. So there wasn't any discussion. This year we were really lucky. It was extremely clear which was the most influential paper of ICSE 2013. And the winner is?
And the winner is SEMFIX, a program repair via semantic analysis by Dityan Nguyen, Dichu, Abik Rochaudhry, and Satish Sandra. And so this paper was really looking at symbolic analysis techniques to support automatic program repair, and it really led to a new direction to how using symbolic execution for specification inference. And we're very happy that 2 of the 4 authors are actually able here to come join us to accept this award. So please come.
Okay, good afternoon. Can you hear me? Okay, thank you very much to the committee for judging our paper worthy for this very prestigious, most influential paper award. We are very honored. I'm Abhik Rochaudhry from the National University of Singapore, and I will also be joined in this talk later on by my co-author, Satish Chandra. So this paper, as was mentioned, was the SEMFIX paper, the program repair by semantic analysis. It was co-authored by 2 other student authors who are currently not in academia, but they are doing well. So when I informed them, one of them told me, well, I'm now the CTO of a scale-up, not a startup, but a scale-up in Shenzhen, China, and we are doing static analysis and security testing, and I'm now employing 110 people. So even though they are not in academia, this is certainly a good moment of pride to also celebrate their achievements. So let's talk about program repair, which is what this paper is about. In program repair, you have a buggy program and some correctness specification, and the correctness specifications, usually the setup that I'm talking about is in the form of test cases, and then you produce a patched program. The applications of program repair are myriad. For example, it can be in education. Let me try to use the laser pointer here. It can be in education, so this is something we have our own homegrown system at the National University of Singapore, for example, where we teach software engineering in the form you would teach operating systems. So we give out a base intelligent programming, intelligent tutoring system, and then every year the students do projects, and then this intelligent tutoring system gets deployed in the first year programming courses. So it's really a real life setup where the teaching of the software engineering project is a real life software engineering project, and this is for giving feedback as well as automated grading to students, and the core of this system is really program repair. So all of the techniques that I will be covering today really form the core of this system. It is used quite a bit for, of course, for correctness, for improving developer productivity, and it's used quite a bit for security vulnerability repair. So in fact, we have, and several others, not just our group, but many other groups have used it for security vulnerability repair, because the exposure of the software systems to security vulnerabilities is large if you don't go for automated repair. It can easily take months. So to give a retrospective of how we started coming into this idea, just a little bit of it. So before working on repair, at least I was working on the debugging problem, and both the debugging problem and the repair problem, the core of the problem really comes from the lack of specifications, because oftentimes you don't have very good specifications to work with. So if you don't have any formal specification and yet you are stuck with a software system which you somehow have to root cause the errors or fix the errors, then what do you do? So on the right-hand side of this slide, you actually see this view graph. This is from my talk in FSC 2010 in New Mexico, so about 13 years ago, where we actually used symbolic execution for debugging, where we compared the embedded Linux, the BusyBox embedded Linux with the GNU core utils, and actually used that to root cause many crashing errors. And we were extremely happy and extremely proud, but the thing is, oftentimes you don't have a reference implementation like this. So this is really what led us to this idea that instead of depending on reference implementations, how about tests? And can you extract really use symbolic analysis to extract specifications from tests and use that to guide the repair? So this is really the first time we presented the paper. Actually, this was presented prior to ICSE in a Darkstuhl seminar in February 2013. You see many familiar faces here, and if you want a spot the author contest, we are right here in the middle of this picture. So the main idea was to use repair by exploiting symbolic execution technology, because you really have test cases. Tests are incomplete specifications, we all know. So you want some generalization capability from the tests. So we are using symbolic execution to do that generalization. And what this comes as a very big advantage is that this gives us scalability not just with respect to the program size, but scalability with respect to the search space size, which is very important in repair, because you might have to consider many edits. We in fact do repair via constraint solving, and we do not depend on any formal specifications being available. Here's a very simple example, which I will go through quickly. So this is intuitively obvious. We all know what a triangle is. It takes in the three sides of a triangle and returns the kind of triangle. So in this case, there are several bugs in this program, but the definition of the isosceles triangle is incorrect. And we have a typical test suite that is given: one for an equilateral triangle, three for the three possibilities in an isosceles triangle, and one for a scalene triangle. So in this philosophy of generating specifications for tests, what you will do is very different from the way symbolic execution is normally used. So you would actually do concrete execution of the tests and not symbolic execution, but somewhere down in the middle where you want to fix the error, which is essentially an unknown expression, you will convert it into an unknown function and infer some tiny properties about this function. So for example, for this test 2, 2, and 3, it will infer the property that I don't know anything about this function f that needs to be inserted here for the isosceles triangle, but it should at least return true for 2, 2, and 3. And if you capture enough of these tiny properties over enough number of test cases, you can use like a synthesis engine or even a search engine in the back end to generate the appropriate expression. And of course, this can be scaled up to multiple line fixes as well. So symbolic execution, I will comment a little bit about symbolic execution. Symbolic execution is a very established technology. It was first proposed in 1976 in this paper, Symbolic Execution and Program Testing, which appeared in Communications of the ACM. And since then, tremendous amount of advancements have been done, a lot of wonderful research on using symbolic execution for testing and verification. I would like to take a moment to highlight that the use of symbolic execution that we have is really very, very different. We do not have any execution with symbolic variables representing the input variables. The only symbolic variables are the patch variables, and essentially this would be a higher order reasoning. This would be at least a second order reasoning because it is an unknown function, but we are converting it into first order reasoning. We are introducing this variable x and getting properties about this variable x. So here I'm just showing how the symbolic execution for testing for this program will proceed. You would have essentially for each of the paths in the program, you would have a leaf node. And the important point is the symbolic variables A, B, and C. These are really the input variables. So here in this view graph, you can actually see the two sides, so to say. So on the left-hand side, you see the symbolic execution being used for repair. So where actually I'm feeding in concrete test cases, and then I'm getting some properties in terms of the symbolic variables that represent the patch variables. On the right-hand side, you see the test generation, where really speaking, the only symbolic variables are the input variables. So in summary, just to kind of summarize this portion of the work, so we would like to place our work with respect to other works in program repair that have taken place. So there are works on search-based repair. Our work essentially started off this domain, I would say, on semantic repair, where instead of doing an explicit search over the space of patch candidates, you really try to get a constraint that represents all the possible patch candidates that would pass these test cases and also other similar tests by generalization. And then you would try to synthesize code via constraint solving at the back end. There are also other kinds of works on learning-based repair that have happened in the meanwhile, which essentially try to prioritize the patches. So in terms of a schematic, we would consider this schematic where essentially we go through the tests, generate a repair constraint, and then consider the conjunction of all of these repair constraints for the purpose of guiding the synthesis or the search in the back end. The important point with respect to this particular contribution is that we want to address the issue of patch overfitting. In the program repair community, this is something which is considered very, very important because you have essentially test cases, and from the test cases, you would like to generate patches which do not overfit the test data. So this way of generating the constraint and then trying to solve the constraint to guide the patch generation process provides a very nice solution to the patch overfitting. My co-author was supposed to take over from here. Yeah, Satish. Yeah.
Thanks, Avik. All right, thanks, Avik. So SEMFIX was 2013, and we thought that it would be a good idea to briefly see what has happened in this domain since then. So one of the things I think all of us will agree on, major change that has happened in our field, in our community, is machine learning making significant inroads in the space of software tools. And I think, the two main reasons is that there is a lot of code out there to train on, including code versions and whatnot, and there has been tremendous progress in the space of machine learning itself, especially deep learning and all the compute power that we have available today. In any case, this has sort of revolutionized the field to some extent, and we had several talks already at the conference about code completion, but in addition, we have used machine learning for code search, for troubleshooting, and of course for automated program repair, as Avik already mentioned. And one of the things that I find fascinating is that the impact of machine learning in our field went from sort of research to mainstream very, very quickly. Now let's talk about a little bit about how machine learning comes to automated program repair. I see the ED is in smaller font. That's a candidate for repair, it seems. So when we think about program repair, the data that you have is actually the corpus not of code, but of code changes. So if you preserve every revision, every commit version of the code, not just you, everyone else has deposited on in code repositories, you can actually mine those changes out, and that become your training data, because that's a wonderful source of edits. It's a distribution of edits that people have made in the past. Sometimes you also know which bug symptoms those edits were about, but it's not necessary to always know that even. And so once you have this distribution of edits, then the machine learning problem is given the context of a buggy code fragment, what edit do you want to predict? And from that point, the story becomes sort of similar to how we have done program repair without machine learning, in the sense that we still tend to have to localize the error as before. Instead of doing a search-based or a semantics-based technique here, we would predict and edit. That's different. And then you still have to validate whether the patch that you applied is in fact the correct patch under a certain definition of correctness. And the picture on this visual essentially just simply focuses, look at the right side picture here. So we are using learning-based repair methodology in addition to fault localization and all of that. The patch verification is not shown in this picture. So I would like to take a few minutes to speak of two industrial, I work in industry. I would like to speak of two industrial projects or projects done in industry relating to program repair. The first one was work that my team and I did at Meta. This work is called Get a Fix. This is about 2019. And here the observation is that if you are looking at version history and if you're looking at errors reported by, let's say, another tool such as a static analysis tool, you know between these version saves whether new warnings were added, that's in green, or whether warnings went away, that's in red. So when warnings go away, it could be because you fixed the warning, or maybe the code that had the warning was deleted for whatever reason. But let's assume that we are fixing warnings. And so if you have a large number of these saved over millions and millions of version changes, you can formulate, collect pretty good training data for what it takes to fix these kinds of bugs. So for a very quick example, what am I doing here? That's not, okay. So for a very quick example, you can think of this simple fix, in air quotes, of a null pointer error where someone wrapped this call to a method in a null check. Okay, so this is a kind of a fix. And now what GetAFix does is look at large number of these kinds of fixes and organizes them in a tree of patterns. and it's a very natural operation using anti-unification. And once you have this tree of patterns, then the remaining problem is that given a new context, how do you predict which patch to apply? And we do that using probabilistic ranking. More details are in the paper mentioned here. So I would like to step back and share what we really learned from doing one of these projects. So one very interesting and surprising thing to us is that developers are really picky about their code. Even if you come up with a semantically equivalent fix of code, it's not necessary that developers will accept it. So here, get a fix resulted in about 40% of fix suggestions accepted, but there is a 9% box that you see semantically equivalent fix. These were fixes that any reasonable person would call correct, but developers don't call correct because they insist on exactly the way they want to fix the program. So that was a very interesting. Second thing is that a lot of techniques in this space do assume that we can try things multiple times. So you generate a patch, you recompile your system, and then you rerun the test and so on. In our context, this was not really an option because of compute budget reasons, and so we had to work very hard on getting just a top-ranked patch and hope that this works. So this may be a lesson for some folks. And then finally, convenient UI integration is super important. Otherwise, the impact of the tool is not realized. So here, for example, I'm showing you a screenshot from the code review system where whenever a static analysis tool reported a problem, GetAfix inserted a suggested patch with options of, hey, do you want to reject this or accept this? And just a very simple UI idea, but this was important in getting suggestions landed, which is good for metrics and whatnot. I would also, I work at Google now. I would also like to mention work that my colleagues at Google has done. This work predates my being at Google, but the idea is in a way similar. This work looks at fixing build errors or compile errors. Again, using similar ideas, you can look at the history of code edits that were instrumental in fixing these kinds of errors. And this technique used neural machine translation to actually generate the fix. The screenshots at the bottom show an example of, you see this red squiggly arrow, that is a occurrence of a compiler warning or compiler error, and the right-hand side is the corrected code. Again, UI-wise, it was very useful to sneak in just a little bit of hint as to where a machine-generated fix may be hiding, so you can click, observe it, and land the fix. Okay, so enough about those projects. Let's step back and see where are the challenges in this field, where ML has helped and so on. So in our view, ML has really helped in generalization of fixed patterns, interpolation between patterns and so forth. So we already saw many talks that were talking about the differences between templates and neural prediction and so forth. This is where machine learning-based techniques have really shown their mettle. The other place where they have ML has helped is, or rather has made a lot of impact, is being productive in fixing static analysis errors and compile errors and things. So narrow domain specification of what needs to be done is easier, but these are places where machine learning has really helped, helped us win. We see continued challenges in the field. Patch accuracy is a problem because tests may not capture the full spec. Patches may be complicated. They may be distributed across many lines or across many functions, the so-called multi-hunk repair problem and so on. Localization continues to be a challenge because you may not actually even know where to make those changes. Nevertheless, what is cool is that within this community, we looked at the number of correct patches computed for defect4j over the last 5 years, and you see an upward trend. That's the bar chart showing on the right. Plotted from 2019 to 2023. Maybe we got the heights of some bars wrong a little bit, that's okay. But one of the problems here is that we are still about 70-something out of 395. So there is ways to go, but we are making progress. Okay, let me now come to the last thing that Abhik and I want to say. So as it has been clear during this conference in our professional lives that coding is undergoing, the practice of software is undergoing a transformation because of availability of these large language models. In particular, a lot of people are using Copilot to write their code and so on. So with these large language models, they are having a profound impact on our community and on research. So a lot of things can be done pretty much out of the box or with few short prompting, and this is quite impressive and making a change in how things are done. So now the question is that as ML, or let's say, instantiated in tools like Copilot begins to generate more code, what is the continued role of APR methods, program repair methods? So here we have a couple of points to share. One is that just because code is ML generated does not mean bugs will not appear. It may be buggy to begin with. Also, if it appears correct, there may be future cases during deployment where conditions might change and a bug might get exposed. So the need for program repair will continue to be there. That said, we do expect models to stop making routine and more predictable kind of bugs. That will just organically happen because of the way the machine learning technology is progressing. Another interesting point to share with you is that as we are all becoming prompt engineers, it's possible that one day prompts will become the source of truth. And really, when you talk about repair, it's about editing the prompt, and the act of repair may migrate upwards from code to prompt. So we'll see if that happens or not, but that's an interesting thought. With that, I'll hand it back to Abhik to share some thoughts on trust. So Abhik, here.
Okay. Yeah, thanks, Satish. So as we move towards more automatically generated code, and we have a combination of automatically generated code and manually written code, the question we feel will remain whether ML generated code will be considered trusted enough to be integrated into a software project. The analogy I have here is that of a self-driving car. We have been hearing about self-driving cars for very long, but we don't see that many self-driving cars on the road because there are a lot of driving regulations. The software industry is unregulated. So you can kind of write risky code, but the assumption is that the code is written by a person, so you can still somehow get back to that person. So there is some informal assurance. When the code is really written by a machine, then that informal assurance is also gone. So what can we do? So we have only a few minutes, so we just leave all of us with some thoughts maybe. So there is increasing amount of work of programs written from large language models. We had a paper right here in this conference, which was presented today afternoon, of automated repair of those programs from large language models, where probably something like Copilot generates the code and then automated program repair is used to improve the code. Now, as a byproduct of that, something that can be done is that the program repair as a byproduct can also produce evidence that the repaired code is correct. So for example, something like symbolic execution or other technologies can play the role of steering the search. Or here you see a tiny video steering the search over the domain of inputs to generate additional test cases, and also do the specification inference over the domain of patches to reduce the space of patches. And then the oracles or the expected behavior of these additional inputs could come from the natural language descriptions, which are now provided. So this is the last slide that we have, that in the world before this LLMs, we had manually written code. We have a programmer. She is sitting here constantly debugging and maybe fixing issues. Whereas when we have automatically generated code, we can have specifications in natural language. Maybe something like Copilot produces the automatically generated code. But there continues to be a role for the semantic techniques, not just to repair the code, because the repair can be done by other techniques as well, but also as a byproduct of the repair to produce evidence so that you trust it enough to integrate it into your software project. So that's our thought, and with that, with this position on trusted automated programming, we would like to thank you for your attention, thank the committee for this very prestigious award, and also open the floor for questions.
I would like to challenge one of the claims that Satish made. So you said that things are getting better because we are fixing more and more of the defects for J defects correctly. So I would like to contest that claim. Please. Because I think what's possibly happening is we're overfitting more and more to the defects for J benchmark because that's the only benchmark we're using again and again. And there's been multiple papers, including one in the SIGSOFT, that has shown that actually when you go to a different benchmark, these techniques that perform better on this version of J, even later versions of J, just doesn't generalize. So I'm not convinced that we're doing better. Are you convinced?
Okay, so let me answer it like this. So when I read these papers, and I have been reading these papers over the last several years, it's not, so there is also new ideas. Maybe the fault is that we don't really have a good supply of benchmarks and so on. But when I read these papers, there are fresh ideas. Many times the ideas make intuitive sense to me. And I believe that if we took a paper from 5 years ago and state of the art now, bring a different benchmark, I think the newer papers will do better. So that's how I would like to answer that. I think Abhik wants to say something.
Maybe, but having said that, I think the larger point of constantly having to evolve the data sets, I think that is very well taken. And in fact, this is probably going to be even more important as we look into this code that is generated from large language models, because the large language models are already trained on a lot of the code data. So this data pollution is an issue, and in fact, even in the work that we have done recently for repair of code from large language models, we curate the data set very carefully so that it was never seen by the large language model. So this is will continue to be an important issue, particularly in the era of LLMs. Yeah, I just wanted to add.
Yeah, of course.
I think in the interest of time, to getting to the reception on time, we'll go ahead and stop now and thank the speakers again for a wonderful, and congratulations.
Thank you. Please come to ICSE 2023 in December in San Francisco.
It is my extreme pleasure to introduce the winner of the Outstanding Research Award. So the award was given earlier today during the award session. So the Outstanding Research Award goes to Gail Murphy for pioneering contributions to recommenders for software engineering and program comprehensions that have impacted both theory and practice. And I'm very pleased to introduce Gail, who is a professor of computer science and vice president of research and innovation at the University of British Columbia, and also the co-founder of TestUp Technology. And her research interests are in improving the productivity of software developers and knowledge workers by giving them tools to identify, manage, and coordinate information that matters in their work. And many people have been impacted by her research, including me personally. And certainly we are very much interested to hear her talk about this SIGSOFT Outstanding Research Award that she has just received. Let's welcome Gail.
It's always really impressive when your slides just actually appear for you. So first of all, thanks to SIGSOFT, thanks to the awards committee, thanks to my nominator and supporters. It really is a privilege to receive this award. And I'm actually going to step out of my comfort zone in this talk because I'm not going to talk at all about the research that led to this award. What I want to do is spend just a few minutes thinking and considering about whether our community is actually asking and answering the questions that we should be to build the software that's highly responsive, highly reliable, of high quality overall, that is able in a sustainable way to meet the needs that humanity has for software. And I'm going to contend a little bit that maybe we're not doing enough about asking and answering those questions in this community. And what better community to be thinking about that than our community? So hopefully I've got the right clicker. I do. And so in this talk, I'm going to rely a lot on a lot of the words of wisdom that a luminary of our field that we lost last fall spoke about, based on his experiences with building IBM OS 360 and other kinds of systems, and being able to eloquently tell us about some of the difficulties that there are in building software systems. So one of the quotes from Professor Brooks is that software work is the most complex that humanity has ever undertaken. And we can argue whether or not that's exactly the case. Is it the exact most complex? But I think together we can agree that software is pretty darn hard to build. And so when we're building it, are we actually spending enough time in our community thinking about that complexity overall? How hard it is to build these systems, and how hard it is to build it in a time where we have so many needs upon us to be able to provide the communication, the software that helps us communicate, the software that helps meet and address people who might have needs to be able to live because they have disabilities of some sort, to be able to build the software that runs our infrastructure, or to be able to build the software that lets us have fun by playing things like video games. So here's the last slide that I'm going to have from my talk. I want to talk a little bit about the essential complexities that there are in building software, reminding us of what those are. Many of those come, of course, from Professor Brooks. And I want to add a fifth kind of complexity that I think is essential, which is the complexity about context. So I'll explain what that means. And I'm going to try to give you a couple of ideas about how in this community we might change what we're doing to better address some of those issues. And in particular, I want to talk about some ways that we might actually think about the holistic problems of building software rather than getting too focused on individual, very detailed parts of software development. I'm not trying to say that we should stop all of that kind of work. It's really important. We've heard great talks today. But we might need to broaden what we're doing as a community to think about the problems more holistically. So the talk is divided into two parts. I want to talk a little bit about what I mean by complexities and by the fact that these complexities have to be solved in the context of wicked problems. And I want to talk a little bit about potential paths forward. So let's delve into the first part. So here's a bit of a timeline. Hopefully most of you are familiar with the No Silver Bullet paper, Essence and Accidents in Software Engineering, which was an invited paper that Fred Brooks published in 1986. It's hard to, in a quote, capture the richness and depth of that paper, but I tried to put one of those quotes on the screen. And what he was looking at in that paper was the fact that there is always something new coming up that, to some extent in our field, purports to solve all the problems, or many of the problems that a field is facing. So the quote is, "But as we look to the horizon of a decade hence, we see no silver bullet to really solve the essential complexities. There's no single development in either technology or management technique which by itself promises even a one order of magnitude improvement in productivity and reliability and in simplicity." And if you think about this in 1986, this is when hardware was rapidly advancing each and every year. And so there was a lot of questions about, can software keep up? Now, I put the timeline at the top to kind of remind ourselves that this 1986 paper, and if you're not familiar with it, suggest that you download it and maybe read it on the likely long plane ride that you have home. That 1986 date, that's only about 20 years since software engineering kind of started to be talked about as software engineering from the 1968 NATO conference. 10 years after publishing that 1986 paper, there was a lot of feedback that apparently Fred Brooks was receiving about the ideas that he had published. And as part of his retrospective book, he included an essay called No Silver Bullet Refined 10 Years Later, where he concluded that indeed he hadn't seen any of those advances that had been purported actually change the amount of productivity we got in software. So what were the complexities he talked about? Well, there was really four. He talked about complexity itself, so a little bit of a recursive concept going on here. And he said software is complex because no two parts of it are alike. We need a lot of parts to build something that matters. And we have this thing called abstraction that we use so that if two parts are alike, we combine them in together. Even with that powerful concept, we still have a lot of parts that get put together to build the software, and as a result, it's very complex. A second complexity he talked about was conformity. If you're building a system that especially is going to interact with hardware components, what is always going to be asked to change? It's not the hardware, it's the software. If you're building a system that's going to go out and be used by people, what changes? not the software, the people change. And I'm going to come back to that point later. The related complexity to that is changeability. Because of its ability to conform, software is continually getting bombarded to change. Even if you have a requirement that was specified, by the time that you try to develop it, sometimes people have tried to change that requirement even before you've been able to deliver it. So the fact that it's infinitely changeable means it's constantly under this bombardment to try to meet the needs of its users. And finally, an interesting concept given David's talk is, and I think you probably have some things to say about this one, is the fact that he referred to software as being invisible. And certainly there are techniques like state charts that help us think about software in a more visual way, but they don't necessarily apply to every kind of software development. They don't necessarily have been adopted by every software development company. And so as a result, we're still in a stage where often the software that is being built is considered to be invisible, and we can debate whether it's unvisualizable overall. If you walk into many software development companies and you ask the developers, what does the software look like, you're going to get different responses. If you ask the management teams overseeing those developments what the software looks like, you probably won't get any answer at all. I also want to argue that there's actually a fifth kind of complexity that we're now dealing with here in the 2020s, and that's of context. Now, context is really hard to define. So let me give you maybe 3 different kinds of context that we need to pay attention to. And one is the build context we're in today. So way back in 1986, one of the hype, the things that were on the horizon that might help was software reuse. And one of the things we've actually gotten good at is software reuse. There's a lot of open source out there that, in fact, development teams rely on each and every day. And those software supply chains that now make up the software that is being produced are getting longer and longer and longer. And we know that the brittleness of those software supply chains is pretty high. If you remember the left pad incident of a few years ago, a tiny piece of software that almost nobody knew really existed in the Node systems ended up taking down the internet when it got pulled from that supply chain. And we know from Sonatype and other kinds of reports that the top 10% of the most downloaded open source projects have the most security vulnerabilities. So we're able with this reuse to build better and bigger software, but at the same time, we're actually in a very brittle state because of the way that we do build it. Now, another kind of context that's important is what I'm going to call deployment context. Another one of the hopes for a silver bullet back in 1986 was the idea of cloud-based systems. If you think about the 80s and you wanted a finance system, each and every organization that wanted a finance system would go to a consultancy or some software development company and ask for a finance system, and they would get one built. It would be deployed to them, they would put it on premise, and they would use it. And they knew what that software mostly did. What we've been able to move to now is to be able to build systems that we deploy on the cloud and have multiple organizations use their own instance of that same underlying system. To make it conform to what an organization needs to do, there's usually a big config, organization, charts, files that help tailor the actual functionality of that system to the organization that's using it. And this is great, right? This is one of the cases where humans now have to change more to the system because you're told, well, we bought this system, it's on the cloud, we can't change it, the humans have to change it. But one of the things I wanted to point out that I think is a problem with this deployment context is it gets really, really hard for the developers of the system and the eventual people who use the system to understand what the behavior is of that finance system they're using. So one thing I get asked to do every year at the university is to attest that we're actually following appropriate financial controls over every research grant in the university, that we have 2-level controls and various sign-offs. When we had the old system that had been built for us, I actually knew that that was probably pretty much true. We've now gone to more of a cloud-based system with lots of config files, and honestly, I have no idea whether or not that's true. And I know based on anecdotes from different people in the university, it works differently for different parts of the university. And so as a user, I would like to be able to query that system and say, is this actually a fact that's true? Or I would like to be able to go to the developers and verify that. But that seems to be very difficult to do with these deployment contexts. And finally, we've talked about this a lot. I'm not going to spend a lot of time on this slide. The societal context that our systems run in has to start mattering to us. Not only are we deploying them with config files, but we're deploying them with data that might have been learned from that the developers have never seen. So in that instance, how are we actually going to go about thinking about whether or not the properties we built into the system as developers are really holding true out there as it's getting used? So I'm going to contend that this idea of context is a new kind of essential complexity, and one that our community in particular, whether it's build, deployment, societal, and probably other context issues you can come up with, is one that we have to start paying a bit more attention to. Now, I actually put in the title the fact that not only do we have these complexities to deal with, but it's also a wicked problem. So a wicked problem is about, the fact that you have something that is almost unsolvable because of the interconnected and tangled nature of everything that makes up that problem. And obviously, when we're doing software developments, and in particular in this community, we think a lot about the technical aspect. We've actually gotten reasonably good at thinking about all the artifacts that make up a system, how they're interconnected, how can we reason about this interconnected web, how can we think about properties that span the many technical pieces that build up a system that's deployed. That technical system is built by an equally complex interconnected web of people. There's developers, there's testers, there's requirements people, there's users involved in that web. And we have some work that thinks about the complexity of that, interconnections and how hard they are. But we don't have near as much work that thinks about the interaction. What are the appropriate organizational structures that we need to be able to manage all of these complexities when we have so many different pieces of technical artifacts, so many different people that are involved in the mix of actually developing it. So I think we have to pay more attention to that. So hopefully that lays the stage a little bit to say we've really got to think about how we are going to manage how hard it is to develop software, and to do so in a way in the context of the socio-technical instance that exists around it. So what can we do about it as this community? Well, we've got these essential complexities, and I bet if you go through a lot of the papers that are in the proceedings, you'll see something in the introduction that relates the problem in the paper to something that's kind of like one of these complexities. So I threw up a couple of example areas of software engineering research at a very generic kind of level. I'm sure we'll have papers, again, probably have some here, that might ask questions about Stack Overflow. What should Stack Overflow questions be like? What might we learn about them? And in that introduction, it might say something about, to help developers change software better, we should da-da-da-da-da. If we have a new method for requirements analysis, it might argue that it's going to reduce the complexity of the software development by having a better specification to be able to rely on. Maybe if we have a paper about fairness testing, it's going to refer to changeability, and so on and so forth. You see time and time again some indication of a generic connection to these essential complexities. But I think we have to start going further. We have to start thinking about what we're not asking. Are we thinking enough about whether there's evidence after that initial appeal to an essential complexity about whether there's been impact over time on actually reducing that complexity? Do we need to actually follow the introduction of something like program repair to see whether there's benefits over time? What do those benefits look like? Do they look like what we anticipated, or are they completely different? And I think Professor Harlan did a really nice job of thinking back over time and seeing how things, his state charts affected things over time. And do we adequately compare these new ideas on large systems? Do we actually look at a particular technique that we're introducing and see how it worked out on 4 or 5 big systems? Over the last 30 years that I've been part of this community, I think we've gone an awfully long way in going from thinking about largely anecdotal system descriptions to starting to hone in on particular aspects of describing where we might have tried one of our new techniques. So today, if you read a paper, you might see some context description about the system that a particular technique was applied to. It might talk about the static and dynamic artifacts, like how many lines of code was it, how many microservices were involved in the system, and it'll probably tell you a little bit about the development context. How many developers were there? How many bugs were open in the system? Metrics like that. I think we need to go a little bit further. I think we need to start thinking about this context capture in a more holistic way. And so what if, as part of trying out our techniques in an open source system, we were able to describe a little bit more about the development context? Maybe we could say something about the requirements process at play in that system. Or maybe something about how many design artifacts were actually there and what they look like. Or what was the team size in terms of not just the developers, but everybody involved. Talk about a little bit more about what the system is so we can start to understand when the techniques that we're developing may or may not apply. I also think we need to do a lot more in situ study. This was actually a lot more common, I think, when I joined software engineering research 30 years or so ago. There was a lot more, perhaps anecdotal descriptions, but descriptions of how someone had worked on aircraft control systems, as Parnas wrote about, or as we heard this today, that there's been inspiration taken from. There was more descriptions of things like OS 360, et cetera. How can we do more of this in situ longitudinal studies of software, whether it's open or closed software, where we can better understand how a technique plays out over time and how it plays out within a particular kind of context. Now, this is not easy, right? This requires a lot of hard work in this community. It's really, really difficult to start thinking about how do we assess results that are going to only be seen over time. That would take us as a community looking at results differently. We might have to convince funding agencies to actually fund longitudinal work, which at least in my experience, they're not very good at. And we might have to convince companies or governments to let us in as academics and maybe not working in industry to be able to try things out in systems. And perhaps publicly funded software that governments often seem to struggle to produce might be a place where our communities could make a real difference. Another idea is, what if we built things more together? What if we actually had test beds that we were building, more than just collecting data out there, to actually put our techniques in practice, see how they work. Again, this is really, really difficult. It's longitudinal. You might not get an answer in a month or 3 months or 6 months, but you'd need to follow things over time and try to understand how they work when software is being grown and evolved and we really hit some of those essential complexities I referred to. So I'm hoping maybe over some fun tonight, we'll be able to start a discussion about how we can actually better study techniques that can try to tame the essential complexities of software development. Really what I'm appealing to is, let's try and not just focus on an individual technique, but start to follow some of those techniques. Start to understand, as I said, how they can work together and how we can make a real difference in how software is going to be developed tomorrow. So hopefully we can figure out how we can do some of this longitudinal study of software in situ at scale, whether we're doing it in conjunction with people that are building other systems or whether we're actually doing some sort of reflective look back at software we're constructing ourselves. So obviously there's a lot of people I want to thank. I have some of their pictures here on the screen. I do want to thank my PhD supervisor, David Notkin. We lost David 10 years ago last month. It's still something that, I probably choke up a little bit about because I miss David. I miss his wisdom, I miss his humor, and I miss the fact that he really cared about this community and was there for so many of us to bring us into research and to keep us in research over time. I've had an amazing set of graduate and undergraduate students that I've had the privilege to work with and postdocs. Some of my PhD students are there on the screen. Hopefully some of them are familiar to you. I've had great colleagues in this community. It's been a wonderful community to be a part of. And it's a community that not only am I impressed by the insights people have and the hard problems that they attack, but just what a wonderful community is to be a part of. I have colleagues at the company that I co-founded, TestUp, that taught me about what big software is really like. And I do want to obviously thank my family who puts up with me not being home nearly enough. But all in all, it's just been so much fun to be part of this community, to be in a place that's challenging and really open to new ideas. So that's what I wanted to say. I wanted to say that hopefully we can figure out how to start not only looking at problems in very little slices and silos, but to start putting them together, understand how we can combine them together so that we can really be the community that helps develop the software of the future. Thank you very much.
We have time for questions.
I just wanted to pick up the glove you dropped. I actually corresponded with Fred Brooks quite a bit. His paper appeared, I think, the same year at the State Chart. He and Exeter Dijkstra were maybe the most famous, strongest opponents to visual languages. Fred Brooks actually wrote, I think I'm quoting it almost exactly, that visual languages are a favorite topic for PhD dissertations. Nothing convincing and definitely nothing of importance has ever come from them. I am convinced nothing ever will. To his defense, I mean, he's no longer with us. After corresponding with him, he essentially thought about flowcharts and things like that. Interestingly, so these are two, as you said, luminaries, both Turing Award winners. Two other famous Turing Award winners, Milner and Hoare, both much later on decided to build visual languages of their own. You can look them up. But I agree that Brooks's paper was remarkable, and I second Gail's recommendation. Go and read it. It's a wonderful piece of work.
And I also recommend reading the 1995 one, because I think he talks about that interchange with you in the paper. So a wonderful thing to read now. Thank you.
Okay, Gail, congratulations and thanks for a wonderful talk. For one point, you said like we really need to build our own system to really gain the first-hand experiences. I think the question is how, as a community, as you know, a lot of things would happen when the incentive system is in place. I think as the current research community, let's look at our PC of ICSE. How high percentage of the PC member actually wrote non-trivial amount of the code, right? I think for new generation students, I mean, with the culture, of course, with a lot of data around now, ChatGPT, it's faster for you to just be an observer rather than the doer. I think like for a lot of points you mentioned, I fully agree. We really need to get our hands dirty to have a lot of experiences and then have the observation. So I think my question is how? Do you have any concrete ideas? Thank you.
Yeah, I mean, thanks for that question, Tao. I think it is not that we have to build our own things, but I do think that we have to be more in connection with either the people who build them or in getting involved, like I said, maybe in publicly funded research, publicly funded systems that get built. So we can be the observers. We don't necessarily have to be the doers, and it wouldn't be everyone in the community, because we have people that are very strong theoretically. We have very strong people that are building things. But I do think that we need to start making more of us a connection to how software actually looks when it's being built, when it grows, when it gets ugly, and understand how we as a community can bring those insights back into our papers. I think we have to do more of that together, and I think we've maybe swung the pendulum a bit more to individual results, a little less away from the big system developments of the past, and we have to find a balance in there somewhere.
Maybe I'll follow up on that. I think my implication was that if you look around the PC discussion or PC reviews, right, we may not show enough appreciation on the so-called system side of the contribution or engineering side of the contribution, which has been quite highly emphasized and appreciated in the system community, like operating system, or like even in the computer architecture community, to my understanding. So then naturally, like when we talk to students, oh, have you talked to the actual target user of your system and to see how they feel? They may just say, no, I haven't. I mean, I have just done enough to get the paper accepted, right? And for the actual mileage, it's not appreciated by the community. That's why I mentioned this incentive system is very important.
So I do think the incentive system is very important, and you know what? I hesitate to say we have to start some new ways to recognize this kind of work, because it's already going on. But we have people focus more on small, incremental publishable units in general than we do in recognizing the long-term, larger impacts. And I think as a community, we can decide to do more of that and actually recognize more of the kind of work that's going on and invite it in so we can learn from it.
Thank you.
Hi, Gail. Thank you very much for the talk. Very, very nice and interesting, and I agree with a lot of the things you said. One of the things you said was that we've got quite good at understanding the artifacts on the technical world, and perhaps, you know, we need to focus more on the social side. And when you talked about the social part, you talked about people and not about organizations. And I was wondering, you know, my feeling is that organizations actually play a big role. They have big agendas, and they set the agenda, the research agenda, and the technology agenda a lot. So how much of that should we be looking at?
So I guess I think of the organizational issues more in terms of, you know, the way that people, the way that companies organize their teams has an incredible effect on how the software gets produced, what the software ends up looking like. We don't look at that very much anymore. Whether or not the incentive structures, that starts to get into corporate issues that I think can be harder for academics to go in and look at. But I think there's smaller steps that we can take to start getting more into that social side. But great question, Seth.
My question may have been answered when you talked to Tao, but I'm still going to ask, because I want to ask you to talk to the authors of papers, not the reviewers. It's about the context. I remember my first DSC paper was a result of 3 years of work, a longitudinal study with the same company, where we studied improvements in the requirements processes. And we thought that introduction of one process would solve all the problems, and it would be an easy paper to write about. It was about every other thing that was going on, the way they were testing the software, they were collaborating with customers, with other processes in the company, what tools they were using. So it was really the context that surrounded the implementation of new things in the company. But it took 3 years to collect data and publish. So my question is, how do we motivate authors to not slice pieces of their research so that they publish every year 15 papers, to have that patience to publish something that is of a bigger impact?
That's a great question. I mean, it obviously starts with so many things. If it's academia, it's promotion and tenure process. We can go through grants, the whole 9 yards, right? However, we don't make any distinctions in our community really that much about being able to describe something very long and large and a little messy. Sometimes that's hard to get accepted. Sometimes you don't have the space or the richness to be able to describe that, versus something that is more, shall we say, cut and dry, or fits in a particular mold. So I think we can look at what we ask papers to be as part of considering this. I think it's also one of those things that as you get maybe later in your career, it's easier to think about doing. Because when you're early in your career, there are different pressures, and we're not going to change the whole system. But over time, there might be places where you can start being part of one of these longer projects and work it out through time. When I look back at our individual research results, and I'm really proud of many of them, I decided not to talk about them, because it's like, well, we've talked about them. We could talk about them again. But really what we need in the community is to start thinking about what are the questions that we are really not asking, that we should be expected to have answers for. And if I'm speaking to somebody in government, it's reasonable for them to ask me, this collection of techniques, how have they worked out in practice? Some people in this room will have great answers. Not everybody will. But I think we need to do better in showing that we are the place that will give you those kinds of answers.
Maybe we get one last question.
Hi, thank you so much for your questions. I'm a PhD student. I have still 5 years to complete the PhD. And the things you are discussing is too broad for a PhD student to think, because we also, I guess you partially answered my question, because there are a lot of pressure to have few publications so that you can defend your thesis. And but do you have any suggestions how to think broader? Because I sometimes my advisor asks me, what is the bigger problem that you're thinking? And I don't want to think bigger because it takes so much time and energy and patience, and I want to publish. I think this is the problem with most of the PhD students. So how do you, if you have any suggestions how we could optimize like both sides in thinking the bigger picture and also like publishing and,
Yeah, great question. I think if we focus on the problems that are really difficult in software development, there's often a way to take your result and try it somewhere in actual industry. It doesn't always work out. I had the luck of being able to do that for my PhD, but the reviews for my PhD work were always, it's a really simple idea. Maybe it's too simple. But it's simple enough to try, and it makes a difference. So I think the more that we can get down to the true essence of a problem, look at state charts, right? It got down to the essence of a problem, and then you can start applying it in many ways. That's a hard thing to hear as a PhD student. I have these arguments with my PhD students all the time. How do we actually get down to what is the question that you're trying to answer? How can you push it through? And when you have that push through results, I would say in my experience, it's always made a big difference to be able to say it actually, this is what is going to be changed, and I can show you how it can get changed. But happy to talk with you again later. I'm standing in between you and dinner. So.
Let's thank Gail again and congratulate her for an insightful talk.